All right, so today we're going to take a look at the double number identities. And from the lecture course of our home, the lecture notes page of our course, I'm going to pull up the section 9.3 set of notes. And I'm actually going to pull up, okay, I'm going to go on the formula sheets. I'm going to pull up the all exam formula sheet. And I believe these are all the two items that we're going to use for today. So up until this point, we have taken a look at the reciprocal formulas, quotient identities, the Pythagorean identities. In the last section, we had taken a look at the sum and difference of cosine, sine, and tangent. And as we were doing the sum and difference of tangent formula, there was some rationalizing the denominator. All right, there's going to be a little bit more of that today. And we're also going to take a look at the double number identity. So if you look at the very first formula, that is read as the double angle for tangent, or the double number for tangent. And that's equal to 2 times the tangent of A over 1 minus tan square A. Notice that the double angle, or the double number for cosine, there are actually 3 formulas. Right? The very first formula says cosine square A minus sine square A. In order to use that first double number identity, you must know both the sine and the cosine. The second double number identity for cosine says 2 cosine square A minus 1. In order to use that formula, you only need to know the cosine. And then there's the final formula for the double angle of cosine, and it's 1 minus 2 sine square A. All right, so in order to use that particular formula, you must know the sine value. Okay, so the formula that you use, it pretty much depends upon the information that you have. And then lastly, we have the double number for sine, right? And that's equal to 2 sine A cosine A. Now, this is not necessarily a proofs course, but if we look at the section 9.3 notes, they sort of give a light proof on how the double angle for cosine formula, at least the first one, is derived. And it's actually derived from the sum of cosine formula. Right, so if you look at the very top, it says that the cosine of 2a, that's equal to cosine a plus a, right? Because a plus a is 2a. Then the sum of cosine formula is used, right? So the sum of cosine formula, okay, just going back momentarily, right, is this first formula. It says cosine a plus b, that's equal to cosine a times cosine b minus sine A sine B. But in our example, we're using A plus A, so we would simply substitute A for all of the angle measures, right? So instead of cosine A cosine B, for B, we're going to substitute in A, right? Because we're using A plus A and not A plus B. All right, so notice once you substitute in A in the formula, cosine A times cosine A is cosine squared A minus sine squared A. Right, and that pops out that first formula. The other two formulas come from the fact that you can rewrite cosine squared A, right, as 1 minus sine squared A. So I'm going to go back slightly. I just want to show you all where this stuff is coming from. I'm going to go to the Pythagorean Theorems. Right, so notice that if you were to take the Pythagorean identity, right, sine squared x plus cosine squared x is equal to 1, we can actually solve it for sine squared x, right? So sine squared x is 1 minus cosine squared x. You can also use that Pythagorean identity to solve for cosine squared, and that's equal to 1 minus sine squared x. Right? So in one of those formulas, sine squared x is replaced with 1 minus cosine squared x. And in the other alternative formula, cosine squared x is replaced with 1 minus sine squared x. All right, so that's actually what happens on the very first formula. Right. Okay, where am I? So here, sine squared a can be substituted with 1 minus sine squared a. Right, so you have a 1 and then negative sine squared a minus sine squared a, well, that's where the negative 2 sine squared a comes in, right? So out pops this formula. And then for this alternative formula, the other alternative formula, sine squared a was substituted for 1 minus cosine squared a. And then out pops this formula, right? Cosine, the double angle for cosine is equal to 2 cosine squared a minus 1. All right, so just in a nutshell, there's 3 formulas to use, but the formula that you're going to use depends upon whether or not you know both the sine or the cosine values. Right. And then lastly, there is the double angle for sine and a double angle for tangent. All right, before we begin, hopefully OneNote is not going to crash to the ground like it's been doing. I want to do an algebra review, and let's see. We are going to rationalize denominators. All right. So, for example, if you have 1 divided by 2 square root of 2, right? So here again, to rationalize the denominator means we only want rational numbers in the denominator. A rational number is a decimal that never stops, never repeats. Excuse me. And a rational number is a number that has a terminating decimal or it repeats. All right, so rational numbers have a terminating decimal or a repeating decimal. All right, so here are some examples. 5 is a rational number because it has a terminating decimal. So let me explain terminating decimal. In the number 5, the decimal is 5.0 and it stops, right? So that's what a terminating decimal means. So 5 would be a rational number. Also a number that repeats, for example, 1/3. Right, so 1/3, if you were to decimalize that, I believe that's 0.333. That keeps on going, never stops, it never ends, but the decimal repeats. These things are considered rational numbers. The square root of 4 is also a rational number because if you decimalize the square root of 4, you get 2.0, right, which is a terminating decimal. Let's see, also, all right, so I think we'll kind of start with that. Irrational numbers. Okay, so when we rationalize the denominator, we want a number that has either terminating decimal or repeating decimal. Irrational numbers have a non a non-terminating or non-repeating decimal, right? So the decimal never stops and it never repeats. So here are some examples. The square root of 2. Any root, right? Because we got square roots, cube roots, fourth roots, fifth roots, whatever. If it's not a perfect root, then it's an irrational number, right? For example, if I were to put the square root of 2 into the calculator, and I should have had all of this up ahead of time, but if I were to put the square root of 2 into the calculator, all right, so that's the square root of 2 into the calculator. Right, notice that the decimal, it never stops, it never repeats. That is an irrational number. Right? Square root of 3 is irrational, right, because it's not a perfect square or perfect, but it's not a perfect root. But the square root of 4 is, right, because it's 2.0. Other irrational numbers are pi, right? Pi never stops, never repeats. All right, so when you rationalize a denominator, right, we want to take the square root. In this case, we want to take the square root out of the denominator. So in order to do that, I'm going to multiply the numerator and the denominator by the square root of 2. All right, keep in mind that anything over itself is 1. So when you multiply anything by 1, you do not change the value, but you can change the way that your term is expressed. All right, so from this point, I'm simply going to multiply the numerators and multiply the denominators. So 1 times the square root of 2 is the square root of 2. Right, 2 square root of 2 times the square root of 2. Right, for this denominator, my coefficient is 1. Right, so I can only multiply coefficients. So 2 times 1 is 2. Square root of 2 times the square root of 2 is the square root of 4. Right, the square root of 4 is perfectly 2. So we have the square root of 2 over 4. All right, so notice now in the denominator, right, we do not have a irrational number. All right. All right, so we will be rationalizing denominators in this section. All right, so I just wanted to review that quickly. All right, so this is an example. This is similar to 3.3 problem number 1. All right, and it says that if, okay, I'm actually just pulling this up on another screen. We're asked to find the exact values of the sine of 2x, cosine 2x, and the tangent of 2x if the sine of x is equal to 1/3 and x is in quadrant 2. All right, so I'll give you a second to write that down. All right, so where do we go from this point? All right, so we're asked to find the exact values for the sine of 2x, the cosine of 2x, and the tangent of 2x. So the first thing I'm going to do is refer to the formula sheets, right? So the first thing we're going to try to do is find the sine of 2x. I'm actually going to write this over here because we're going to have to do a triangle sketch. So we're going to find the sine of 2x. So I'm going to bring up the formula sheet. And if we look at the formula for the sine of 2a, all right, so we're just going to replace a with x. That's equal to 2 sine x cosine x. Right, so the sine of 2x is equal to 2 sine x cosine x, right? So we were given sine x, so sine x is equal to 1/3. So I can actually put in 2 times the sine of x, which is 1/3, times the cosine of x, which I do not know, right? So we're going to have to sketch a triangle. Okay. Now we're sort of looking at the view an example. And I think there's a simpler way to do the problem. We're going to do what's called a triangle sketch. And we're just going to sketch out this angle x, right? So we're given the sine for x is 1/3. And we're given that x is in the second quadrant. So I'm going to sketch out an angle. So keep in mind that all of our angles start along the positive x-axis. Right, I'm going to drop my perpendicular and a right triangle is formed, right? So this is our angle in the second quadrant, and that's x. All right, so we now have an x, a y, and an r. Okay, we were given the sine value, right? The sine of x, or the sine of any angle measure, is y over r, right, from our formula. So we're given that the sine of x is 1/3. So this means that our y value is 1 and our r value is 3. Okay. And we have to find out x. All right. So remember, we did have a formula. X is equal to the square root of r squared minus y squared. So r is 3. So we're going to square 3 minus y, which is 1. We're going to square that. 3 squared is 9. 1 squared is 1. So we have the square root of 8. Okay, keep in mind, anytime we deal with radicals, and I forgot to do this in the algebra introduction, but we want to make sure that all radicals are simplified. All right, so I'm going to kind of go back. I'll give you a minute to copy this down, and I'm going to kind of review how we would simplify the square root of 8, because there's a lot of things radicals, you must simplify all radicals. So I'm going to kind of go back up for a second. And I'm going to do that over here. And this is to simplify radicals. And it says that the nth root of a times b, that's equal to the nth root of a times the nth root of b. All right, so, and this formula can also be used in reverse. So here's the setup for a radical. All right, first we have the radical sign. Right, we have an index. Now, if you don't see an index, it's automatically understood to be a square root, right? There isn't like no first root or anything like that. It's either, if you don't see an index, it's a square root, but we do have 4, 5, 6, 7 roots, so on and so forth. All right, so n is the index. Whatever is underneath the radical sign is the radicand. All right, so that's the basic setup for a radical. So now if you want to simplify a radical, so we're going to simplify the square root of 8, right? I can actually rewrite the square root of 8 as 2 individual radicals, right? So what numbers give us 8? Well, 1 times 8 is 8, and 2 times 4 is 8. The setup you're going to use would be the numbers that have what are called perfect radicals. So notice if I were to simplify the square root of 8 as the square root of 4 times the square root of 2, right? The square root of 4 is perfectly 2. The square root of 2 is not perfect, so it remains inside of the radical. So the square root of 8 in a simplified form is 2 times the square root of 2. Okay, so what I want to show now is that both of these things, they have the exact same value, they're just written in a different form. So if I were to evaluate the square root of 8, right, I get 2.828. Okay, if I were to evaluate 2 times the square root of 2, I get the same value. Right, so anytime you simplify radicals, you want to use what are called perfect, or anytime you want to simplify square roots, you must use what are called perfect squares. All right, so the perfect square I used here was 4. All right. So once you simplify the square root of 8, that equals to 2 times the square root of 2. All right, but I want you to notice something very, very closely. Notice that when we were working out this math, I actually got a positive 2 times the square root of 2. But keep in mind that I'm using this formula. The formula doesn't actually keep into account the direction, right? So notice my x value here. So notice if this is my point, right? And if I were to actually write out the coordinates for this point, I would start at the origin. I would move to the left, right? So since I'm moving to the left, that actually makes this value negative. And then I would go up 1 unit. So the coordinates for this point should actually be negative 2 square root of 2 comma negative 2 square root of 2 comma 1. Right, that's actually the ordered pair for that point. So notice mathematically we got a positive number, but based on our sketch, that x value should be negative. Right. So now I believe we have enough information to find the cosine. Right, so the cosine for some angle is x over r. So our x value is negative 2 square root of 2 over 3. Right, so we did a triangle sketch, just a review. Right, first thing we did was we picked out the correct formula, the double number for sine, that's equal to 2 sine x cosine x. Right, we were given the sine value, which is 1/3. We were also given the fact that x was in the second quadrant. So in order to find the cosine value, we sketched out a angle in the second quadrant. Right, we dropped the perpendicular. We figured out x. Right, we re-examined the triangle just to make sure our signs were right. Right, we found from the triangle sketch that x was negative just based on the direction we were moving. And from that point, we were able to determine the cosine value. So in this formula, we're going to substitute the cosine for negative square root of 2 over 2, comma 3. All right, and now we're just going to multiply all this stuff together. So I'm going to multiply all my numerators. I'm just put 2 over 1, so 2 times, well, first off, we're going to determine the signs, right? A positive times a positive is a positive, and then a positive times a negative is a negative. If I multiply all my numerators, 2 times 1 is 2. 2 times 2 square root of 2 is 4 square root of 2. And for my denominators, 1 times 3 times 3 is 9. So we have a double number sine value of negative 4 times the square root of 2. Right, so that was based on a triangle sketch. Next, we're going to find the double angle or the double number for cosine. Okay, so I'm going to go back to the formula sheet. And we see that the double number for cosine, there are actually 3 of them. Right? So we have cosine squared A minus sine squared A. We have 2 cosine squared A minus 1, and we also have 1 minus 2 sine squared A. Okay, now I want to try to do as less simplifying of a radical as possible, and I'm actually going to use this formula, right? The cosine of 2x is equal to 1 minus 2 sine squared x. Now, you can use any one of these formulas, okay? You should get the exact same answer, but I believe the formula that would give us the correct solution without too much work would be this formula. All right, so the cosine of 2x, that's equal to 1 minus 2 sine square x. Right, and we were given the sine value as 1/3. Right, so I'm going to substitute the sine of x for 1/3 in the formula. So I have 1 minus 2 times sine squared x. So this is the way I'm going to write that out. I'm going to take the value for the sine of x, which is 1/3, and then I'm going to square that value. All right, so remember the order operations. Please excuse my dear Aunt Sally. We want to do what's in the innermost parentheses, which we don't have. The next thing we're going to do is evaluate exponents. So I have 1/3 quantity squared. So I want to square the numerator. 1 squared is 1. I want to square the denominator. 3 squared is 9. The next thing we're going to do following order operations is to multiply or divide whatever comes first from left to right. So I'm going to multiply 2 times 1/9. So I have 2/9. Now I'm going to subtract 1 minus 2/9. In order to subtract fractions, you must have a common denominator, right? So I'm going to re-express 1 as a denominator of 9, right? Because 9 over 9 is 1. It just has a denominator of 9. When you subtract fractions, you must have a common denominator. So I'm going to keep that common denominator, combine the numerators. So we have 7/9 is the double number for cosine value. Okay, and I'm kind of clear my throat a little bit. And we're going to look at the double angle for tangent. All right, so here we're going to find the double angle for tangent. Right, so if you look at your formula sheet, there's only one formula for the double angle of tangent, right? And that's equal to 2 times the tangent of x divided by 1 minus the tangent squared x. So what is the tangent of x? Right. Well, from our formulas, the tangent of any angle is y over x. Right. So we do have a triangle sketch. Let's go back to that. Right. So we have a y value of 1. We have an x value of -2 divided by the square root of 2. Okay, so at this time, I'm gonna pause the video. I'll write it out first because I at least want you to attempt this before I work it out. So this is 2 times the tangent of x. So I'm gonna substitute it may be best to rationalize this denominator. Right? So if I rationalize the denominator, which was here, right? 1 divided by 2 square root of 2, we kind of rationalize the denominator, and we got square root of 2 over 4. So I just want to show you that these things do have the same value, okay, which I did not do earlier in the lesson. Okay, calculator. All right, so this is 1 divided by, I'm going to use a set of parentheses. I'm going to put in 2 times the square root of 2. and I get 0.35355. I'm going to evaluate the square root of 2 divided by 4. And notice we get the exact same value. So instead of using -1 square root of 2 over 2, I'm going to use negative square root of 2 over 4. All right, so I've simplified or rationalized this denominator. Now you can use either one in the formula, but here I'm going to use the simplified form of the radical. Right, so in this formula, we're going to substitute the tangent of x for a negative square root of 2 over 2. All right, so substituting that in, we have 2 times the tangent of x. And excuse me, that's the square root of negative square root of 2 over 4, excuse me. So in the numerator, we have 2 times the tangent of x, which is negative square root of 2 over 4, divided by 1 minus tangent squared x. So that's 1 minus the tangent, which is negative square root of 2 over 4, quantity squared. So at this point, I'm going to give you 5 minutes or so to attempt to solve this, and then I'm going to return with the solution. All right, let's take a look at the solution. All right, so in the numerator, when we multiply 2 times negative square root of 2 over 2, well, first off, a positive times a negative is a negative. When I multiply 2 times square root of 2 over 4, the 2 and the 4 are going to reduce down. So in the numerator, I have negative square root of 2 over 2. In the denominator, I'm going to apply the order operations, right? Please excuse my dear Aunt Sally. So I don't have an innermost, well, I do have an innermost set of parentheses, but there's nothing to simplify. The next thing I'm going to do is evaluate the exponent. So I'm going to bring down 1. I'm also going to bring down minus. And now if I look within my set of parentheses, right, that's my base. If I were to square a negative, right, a negative times a negative is a positive. Next, we'll have to square the numerator and the denominator. So the square root of 2 squared forces the square root and the square to cancel, so I'm left with 2. If I square the denominator, 4 squared is 16. So now I'm going to simplify the denominator a little bit more. So in the top I have negative square root of 2 over 2. In the denominator, right, I'm going to do the sort of the math trick I did the last time. I'm going to express them both as fractions. So I'm going to re-express 1 with the denominator of 16. So I'm actually going to write that as 16 over 16. Right? Because anything over itself is 1. It's just a 1 with a denominator of 16 minus 2 over 16. So if we simplify the denominator, okay, so the numerator, I'm going to just bring down negative square root of 2 over 2. For the denominator, since I have a common denominator, I'm going to keep that denominator. I'm going to combine my numerators, right? 16 minus 2 is 14. Right, so I have negative square root of 2 over 2 divided by 14 over 16. Okay. From this point, I'm going to use this formula, A over B all over C over D. That's A times D divided by B times C. So that's going to allow me to multiply the very top and the very bottom, and then the bottom of the top and the top of the bottom. Right, so if we determine our sign first, a negative divided by a positive is a negative. So in the numerator, I can multiply the very top and the very bottom. So that gives me 16 times the square root of 2. I can also multiply the bottom of the top and the top of the bottom. So 2 times 14 is 28. And the last thing to do here is to simplify. Right, so I can reduce 16 over 28. We can divide both of these by 4. Right, so I have negative 4 square root of 2 over 20 over 7. Okay, and this is the double angle for tangent. All right, so on not a lot, but most of the double angle problems, there is a fair bit of algebra in the background. All right, so we did, just to kind of quickly summarize this. Right, we were given the sine value. We were given that it was in quadrant 2. Based on those two facts, we sketched out an angle, we found x, and then we basically did algebra to find the double angle for sine, cosine, and tangent. All right, so when you're doing your triangle sketch, be careful on your signs. All right, now we're going to take a look at a problem that's similar to number 3. Right, so this is 3.3, number 3. And this one says to simplify to one trigonometric expression. And this is 4 times the sine of pi over 4 times 4 times the cosine of pi over 4. Using the double number identities. Okay. Now this actually, using double number identities, that wasn't actually in the problem, but since this is coming out of the double number section, okay, we're using the double number formula to help solve it. All right, so before we go any further, I just want to let you know that when you're using these formulas, you can use the formulas in reverse, and you can manipulate the formulas. So using reverse means I can spin them around. Manipulator means that whatever you do to one side, in order to maintain equality, you must do the exact same thing to the other side. I also looked at the views of solution on this one, and it was not very intuitive. So I'm going to just show another way on how to work out this problem. The first thing I want to do is look at the double number identities to see which formula imitates a sine times a cosine value. Right, so if I look at the double number identities, the only thing that really fits that form is this one, right? Right, because I can clearly see the cosine, the sine times the cosine, right? But the 4 and all that other kind of stuff's not in there. So I'm gonna assume that this is a formula simply based on the fact that there's a sine times some kind of cosine value. All right. So I am going to write the problem in, or excuse me, write the formula in reverse. Two times the sine of x times the cosine of x is equal to the sine of 2x. Right? But that kind of looks clearly different than what I have here. I have like 4 times the sine of x, right? X could be pi over 4, our angle measure, times 4 times the cosine of pi over 4. All right, so I'm going to rewrite the actual problem that I'm given, and I'm going to write it out in this fashion. I'm going to write it out as 16 times the sine of pi over 4 times the cosine of pi over 4. Right, and I'm going to ask, do you agree with what is going on here? Right, I simply multiplied 4 times 4, that's where the 16 comes from, and I just pulled that 16 in front of my sine times the cosine. All right, so these two things are in fact one and the same. So now that I look at it, I have a 16 times the sine of some value times the cosine of the same value. But in my formula, I have 2 times the sine of some angle times the cosine of some angle, right? So instead of the 2, I need a 16. So how could I make this turn this 2 into a 16? Well, I can multiply by 8, right? In order to maintain equality, whatever I do to one side, I have to do the same thing to the other side. So now if I simplify on the left-hand side, 8 times 2 is 16. So I have 16 cosine x, well, excuse me, 16 sine x times the cosine of x. Okay, that's equal to 8 times the sine of 2x. And this is my new manipulated formula. All right, so now they kind of fit. I have 16 sine x cosine x. And in this problem, I'm given 16 times the sine of pi over 4 times the cosine of pi over 4. All right, so above that, I'm just going to write that formula. So I have 16 times the sine of x times the cosine of x. That's equal to 8 times the sine of 2x. Right, so from this point, I'm going to take the formula and I'm going to substitute x for pi over 4. So this is equal to 8 times the sine of 2 times x, and I'm going to substitute x with pi over 4. And if I simplify 2 times pi over 4, that's pi over 2. So this simplifies to give us 8 times the sine of pi over 2. So that was explained a little bit differently if you looked at I believe that problem had a written solution. Yeah, it had a written solution. But notice here, the first thing I did was I multiplied 4 times 4 to get 16. I just rewrote it. All right, these two things are the exact same thing. All right, so now I'm kind of just staring at a sine times a cosine, and I have this coefficient in front. The next thing we did was to identify a formula that fits the pattern, right? The sine times the cosine deal. We modified the formula by multiplying both sides by 8, and out popped the 16 sine x cosine x. Right, we used the manipulated formula to find the value. Right, 8 times the sine of pi over 2. All right, I'm going to go back to the lecture notes for a second. I close it down. All right, and we just kind of look at these other two examples, and then there's like 5 questions in this section, and all 5 questions are sort of algebra heavy. So for the last couple of examples, we're just kind of looking through on the notes, and then when we meet again, I'll actually work out one of the 2 problems. All right, so okay, I thought this was double numbers. Okay, yeah, half number identities. I just want to set up this half number identity stuff because in this section there's, you have to use the double number identities. Those are like the first 3 problems. And then the last 2 problems deal with half number identities. All right, so we're going to just look at the half number identities on the slide. And then when we meet again, I'll work out problem number 4 or 5. All right, so I'm going to go back to the formula sheet just a second. And the half number identities are actually underneath the product, the sum, and the sum, the product. Okay, so we take a look at the half number identities. We have this first formula is read as the double number or the double angle of cosine, and it's equal to plus or minus the square root of 1 plus cosine A divided by 2. All right, so in order to use this formula, you must know the cosine of A. You've also noticed that there is a plus or minus. You're going to use plus if your half angle, which is the angle you're trying to find, depending upon which quadrant is in, if it's negative, you want to use negative, and if it's positive, you want to use positive. All right, so there is a plus or minus in the formula, but you're going to use plus or minus based upon where your angle is. Next, we have the double number for sine. So it says that the double number for sine is equal to plus or minus. So here again, you're going to take wherever that angle lies in whatever quadrant, and you're going to base the sine based upon where that angle is once it's sketched out. That's equal to the square root of 1 minus cosine A divided by 2. So notice that in both of these formulas, you must know the cosine value. And then for the double number of tangent, there are 3 formulas. Right, the first formula says the double number for tangent is equal to plus or minus. So here again, based upon where in what quadrant your angle lies, that's going to determine which sign you use. Times the square root of 1 minus cosine A divided by 1 plus cosine A. All right, so in order to use the first formula, you need to know this cosine value. To use the other 2 formulas, you need to know both the sine and the cosine, but you do not have to determine the sine before you use the formula. All right, so notice closely on this second double angle for tangent, that's equal to sine A divided by 1 plus cosine A. All right, so notice, unlike the other formulas, there is no plus or minus. Once you do the math on these last 2 formulas, the plus or the minus is going to pop out in the math. The last double number for tangent says 1 minus cosine A divided by sine A. Right, so here again, you must know both the sine and the cosine value, but you don't have to predetermine the sine. All right, that sine is just going to fall out when doing the math. Okay, let's take a look at the slides. All right, the lecture notes. So here again, all right, this is sort of how the formulas are derived. All right, they're actually derived from the double number from cosine formula. All right, so once again, here are the formulas. All right, and here is an example. Right, and we're asked to find the cosine of pi over 12. Okay, I'm gonna clear my throat a little bit on this. If they ask you to use a particular formula, because you're gonna see this stuff a lot, right? Like in the first section, I believe you're asked to find this cosine of pi over 12, and you got like a little funky little answer. Depending upon which formula you use, your answer is going to look totally different, even though the numerical value is going to be the same. So I just want to point that out to you because you probably found this before using a sum and a difference, but the way that the solution is expressed is a little bit different. All right. So in this problem, you're asked to find the exact value of pi over 12 using the half number identity. So that means that you must use a half number identity. All right. So first thing I want to do is just change pi over 12 radians to a degree measure just so I can determine which quadrant I'm in. So I believe that's going to be 15 degrees, right? 180 divided by 12 is 15 degrees, right? And you probably found 15 degrees before using the sum and difference formulas, right? 45 minus 30 or whatever angles you're using. And the answer was slightly different. I mean, it was the same numerically, but exactly the value. If you write it out in an exact form, the value is different. All right, so okay, I'm gonna get it together. All right, so here's how this works. So we have the cosine of 15 degrees. Come on. Okay, this is supposed to slide up. All right, so we have the cosine of 15 degrees, right? So what we were doing before using the sum and difference formulas, we would write this out as a cosine of 45 minus 30, right? And you would proceed with the difference of cosine. But here we're asked to use the half number identity. All right, so this is how this works. First off, you want to determine which quadrant the cosine of 15 degrees is in, right? Because remember in our formula, there was that little plus or minus thing. So in order to figure out if it's plus or minus, first of all, we're going to find out where 15 degree lives, a 15 degree angle lives, right? It should be somewhere in the first quadrant. So if I'm in the first quadrant, right, all students take courses. So that means the cosine has to be positive, right? It all depends on where your angle lies, determines the sign, okay? So now if I'm using a half number identity, instead of trying to find 15 degrees, let's say 45 minus 30, I'm going to find 15 degrees by using 30 degrees divided by 2, right? Because 30 divided by 2 is 15 degrees, right? So we've already established that the sign is positive. Now, if we look at the formula, let me go back to the formula. All right, the cosine of a over 2, right, that's equal to plus or minus, and we already established that it should be a plus, 1 plus the cosine of a divided by 2. Right, so we already established that it's positive, so I'm just going to write the formula above the problem. It's cosine of a over 2. That's equal to plus or minus the square root of 1 plus cosine a divided by 2. Right, so in the formula, I'm simply going to substitute a for 30 degrees. So I have 1 plus the cosine of 30 degrees divided by 2. So what is the cosine of 30 degrees? All right. So if you look at your unit circle, or let me just pull that up really quick. All right, if I look at my unit circle and if we look at 30 degrees, which is pi over 6, the cosine is the x value, that's square root of 3 over 2. Right, and now we need to simplify. All right, so I need to, first of all, I'm going to try to clear the fractions. Okay, I have a fractional bar, right, which separates the numerator and the denominator. I want to make sure I get rid of any fractions in the numerator and any fractions in the denominator. So in order to do that, I'm going to multiply the numerator and the denominator by the least common denominator. Right, so if I look at all my numbers, this one has a denominator of 1, so we don't really use ones. If I look in the denominator 2, right, it has a denominator 1. Right? I could put anything over 1. That's a whole number. And if I look for my third term, the square root of 3 over 2, it has a denominator of 2. So I'm going to multiply the numerator and the denominator by 2. Right. Remember, I'm multiplying by 1. Anytime I multiply by 1, I'm not changing the value, but I can change the way that my number is expressed. All right, so I'm going to distribute 2. All right, so I'm still in the square root, so 1 times 2 is 2. If I multiply 2 times the square root of 3 over 2, the 2's cancel, so I have plus the square root of 3. Right, 2 times 2 is 4. Okay, I'm going to go back to some algebra for a second. And I want to talk about the quotient rule for radicals. And it says that the nth root of a divided by b, that's equal to the nth root of a divided by the nth root of b. So what that means is I can take a denominator and I can actually split it up. Right, so I'm going to rewrite this as, and I know this may look funny, the square root of 2 plus the square root of 3. So notice I have like a square root inside of a square root, divided by the square root of 4. The square root of 4 is perfectly 2, so my final result is the square root of 2 plus the square root of 3 divided by 2. Right, and this is where this answer comes in. All right, so there are a couple of more examples here. They're finding, this is like a triangle sketch, which we don't actually do in this course. No, we don't do that in this course. Okay, this is just an example using the formula in reverse. This was taken from a different textbook, so the only example that's pertinent to this course would be this first example. So notice if you look back at your notes, and if you were in, let's say, section 3.1, and you had to find the cosine of 15 degrees using the sum and difference formulas, notice that that answer is totally different than this answer. right? Which means that whenever you're asked to use a particular formula, you must use that formula. All right, so I'm going to stop the recording.